Sorry I was out of town, unexpected stuff, so hopefully you got to play around with some of the ideas of what matter actually looks like at the molecular level, thinking about why it is you have certain molecules that boil or melt at different temperatures. And we're going to spend some time today talking about the third phase, gas phase specifically. Before we do that, we're going to spend a tiny bit of time kind of reviewing some of the things that Ms. Katoum helped you with on Monday. So if you have not already clicked in your response, we only have 15 responses. So you will click on the image and then you hit the send button, just like a numeric answer. So it's asking what's the most polar part of this molecule. Yeah, I'll pull them up in a second. We've got about 35 people here. Once you put your little portion of it, go ahead and see if the person next to you also has a similar response. Or behind you, or scoot over to that. About this? Oh, that's okay. Alright, we have 29 responses. Everyone clicked in? You better get here, Jay. Alright. I'm going to go ahead and pull up the image. I think I have to close it to do that. We only have 29 people? 30? How about sit down, grab your stuff first, bring your stuff out when you have a break, or when you finish a question, then go ahead and grab some food after that. I think that a van pool just arrived. Come join us.
I'm parallel parked like a boss. Like I'm feeling like so.
All right.
I feel like a boss right now.
We're in the middle class.
True New York.
It'd be great.
Tiny spot.
I don't think anybody's focused today.
Like.
Okay, we're gonna have to focus because you know how many classes we have left?
This one.
2.
What? Another one?
I mean,
We should just go over the old stuff.
Counting this one?
Monday's class. So if we're looking at one molecule by itself, how are we going to determine whether, we can say if it's a really small molecule, we can say the whole molecule if it's polar or not. In a bigger molecule, we're looking for regions of polarity. So what are we looking for in a molecule that's this big about where there might be polarity? Why is there a high density of dots on the right side of this molecule?
That's where the energy is.
That's where the OH is, and the other ones are carbons. And so they're not polar because they're attached to hydrogen.
Okay, so what is that hydrogen bonded to?
The oxygen.
Oxygen. That's the most polar bond in this entire molecule is an OH right there. So that end of the molecule is very polar. The most polar bond is the OH, and then it also has a CO and 2 CO bonds. Each of those are polar. So the right side of this molecule, and I don't know if I can select any of these. I don't know how to do it. Whew. That part will be considered polar. Does that work? Kind of, sort of? Okay. Let's look at a second molecule. So the first one was mysteric acid. This is phosphatidyl ethanolamine. So go ahead and choose the target first. compare with your neighbor, what is the most polar part of that molecule? All right, we have almost 30 responses. Let's do a couple more seconds. Ready to close out? Everyone hit send. All right. I wish I could make this a lot bigger.
It's hard to tell. It's that little.
All right, so what are we looking for? OH we know is a very polar bond. So if we go back and we look at our structure over here, we have POH. Okay? That's a very polar bond. Anything else that we might be attracting our attention? So CH2 are those polar bonds. Carbon and hydrogen have very similar electronegativity. That is not a polar bond. Jocelyn? That is the most polar part of this molecule. Remember we said if it's so far different polarity, electronegativity, that it's so polar we call it ionic. So that is the most polar part of the molecule to the extent that it's actually positively charged. However, I would say all of these components here are also very polar because phosphorus is similar electronegativity to carbon because it's about the same distance away from oxygen-ish. So this is all very polar PO bonds and POH and oxygen and carbon. Up here we have some polarity too. Okay. Last question on this topic. Which one of these would you consider the most polar compound? Click in your own response first, and then check next to it. Couple more seconds. Make sure you check with someone next to you. I'll have you ask that. Okay, so I'd really like Dylan to ask this question the whole class, and then we can talk through this.
My question was, because this one over here, phosphatidylphenylamine, has more polar bonds than stearic acid, does that compound just like make the whole entire thing more polar? Of course.
So based on the class's answer, they think yes. So almost the entire class put B as their answer. What else did you talk about in class on Monday related to determining which is a more polar molecule? You had two molecules, you're comparing two molecules, which one's more polar and why? Chris?
The stackability in like the form of the molecule.
Okay, so the shape of it definitely had something to do with it, and so that does play a role. In this case, there's kind of a lot going on, so I don't know if we're going to think too much about the three-dimensional layout. We'll get to that actually in a second. What else, Mel?
Does it have anything to do with the amount of carbons that are in the compound?
It does. Why?
Because carbon is highly electronegative.
It's actually like a medium electronegativity one. So why is it important to think about how many carbons are in the molecule? And not just carbon, but carbon bonded to carbon. So carbon-carbon bonds are nonpolar. Carbon-hydrogen bonds are nonpolar. So remember we said stearic acid. This whole end right here is greasy. It's fatty. It doesn't dissolve in water. Also known as nonpolar. This end is polar. when we looked at the molecules in class on Monday, the first two molecules we looked at, both had the same OH connected to carbon, but one of them had more carbons on it. The one with more carbons was less polar overall as a molecule. It's about the ratio of polar to nonpolar bonds. That was what I wanted the big takeaway to be from those first 2 or 3 slides, is that if you have a higher ratio of polar bonds, it is going to be a more polar molecule. The second set of compounds that you saw had the exact same number of carbons and hydrogens and oxygens in them. They had the same number of carbon polar bonds and nonpolar bonds. Chris kind of pointed out a little bit, they have different shape, and so you would have slightly different properties, but what the high level that I want us at tonight is to look at them and say, what's the ratio of polar to nonpolar bonds? If they have the same types of polar bonds and the ratio is the same, I'd say they're about the same. So, do they have the same types of polar bonds? What did Jocelyn point out? Not only do we have some polar bonds, we probably even have a higher ratio of polar to nonpolar. We also have one that's an ion. So this one is going to be the more polar molecule, although both of them have really greasy parts, all these carbon and carbon hydrogen chains. So does anyone recognize these molecules? Have you seen these in other classes?
Isn't it mysteric acid?
Say again, is mysteric acid?
And so,
Mysteric acid is, I think, part of soap or conditioner, or palmitic acid, which is like one more carbon. So very similar. So I would actually have a hard time answering this question, but I think that positive charge would bring me to say that this is going to be a more polar molecule. But both of them have such large amounts of nonpolar molecules. So have you heard of this thing called a phospholipid bilayer? Is that like been in some biology classes of yours maybe? Okay. Does this compound look familiar? This is a cartoon drawing that you get in biology class. Is you have these long nonpolar chains of carbon, 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 hydrogen. You have this polar region and this superpolar region that's charged, and a lot of times that OH is actually O-. And then they draw them like this, because that's a cartoon version. And then they draw them like this. Each one of these is one of those individual molecules. And you put them together, and they end up forming a phospholipid bilayer. So they self-assemble. And I think I have a little YouTube video that's super cool. Let me see if I can go to it. So this is a super busy animation. What are all these little gray things moving around? Water. Usually we don't show the water. So this animation, they showed water. And they did a computer simulation, a computer model, to see what would happen if we put a whole bunch of those phosphatidylethylamine ammoniums. And those are the big long green chains. And you can see that they have a head on them. And so this is, if we do energy minimization calculations, which is like, find the most stable position every half second. And you give it enough time, and these things find the most stable position. So what are they doing? Why are they putting the green ends together?
Because it's hydrophobic.
Because they're pushing out water, and then which ends are close to the water? These ends. Courtney? So you have the hydrophobic region inside, that if they're out putting in the water, it's actually lower energy because you have nonpolar interacting with polar. Instead, when you have them fold in towards each other, then the things like dissolves like is probably a term you've heard. It's because of energetics, right? So if they end up pointing towards each other, it's a lower energy, it's more stable, and then the polar groups stick out towards the water. So I thought that was kind of cool, just kind of visualize what they actually look like. Is that what you do in your spare time too, is you look at videos like that? I love Tiny Desk concerts, as you can tell. It's always dangerous to have your YouTube history up there, I feel like. Viking videos? What are you? Okay. So, the big take-home, kind of in summary from last class, is we need to be able to look at the structure of a molecule and determine if it is more or less polar than something else. I would give you a much easier example than these two on the exam and say which one is more polar, and then how that relates to this boiling point. And we'll probably spend some time in class on that on Monday. For today, we're going to focus more on the gas phase, and so what things look like when they are actually in the gas phase. So I think these are the three statements here. Go ahead and read through question 1. Each of those three statements determine whether it's true or false. So answer all three of them, and then we'll go through them with a clicker.
What's the definition of movement that we're using? Yeah, what's the definition of movement that we're choosing gas here? No, that's the definition of movement.
People have questions today.
What's the definition of movement that we're referring to here?
Of the what?
What's the definition of movement that we're referring to here?
Good question. All right, we have 29 responses. Make sure you submitted your response. We're doing the first question. So, is this true or false? The first one. A sample of solid water, the molecules are not moving. You think that's true or false? Click in your answer. And there's a split on this, and I think it relates to Chris's question. Chris asked, what's our definition of movement? What's usually our definition of movement? Say again?
I said flowy.
Flowy. So translocation would be the technical term, right? It changes location. If you look at it 1 second, you look at it later, it's in a different physical location. So for this question, let's use that definition. So, can it move from one location to another? And this statement is saying no.
Oh, so we're not doing it like with the Kelvin scale of it. They're still moving all the way down to
It's a solid. We're just talking about individual molecules in a solid. All right, a couple more seconds. Anyone want to change an answer a bit with that definition?
Well, I don't know what to do now.
All right. Closing out. So we have a slight majority saying that this is a true statement, that in solid water, the water molecules do not move. Anyone want to justify that?
Honestly, I'll put it there because it's frozen.
It's frozen. Do you want to build a snowman? So based on the definition of translocation in solid water, yes, you could take the chunk of ice and move it somewhere else. But I'm saying that as they're sitting there in a solid state, those particles are stuck in a crystal lattice. They have a very specific order in a specific position. And until they're melted, they're not going to move from that, or until they're physically busted apart. What about the second one? Go ahead and click in your response for the second one. Sample of liquid water. The molecules are not moving. Let's do 15 seconds for this response.
The container that it's being held in.
Oh, it's liquid water. Come on.
Yeah, but is there a force?
Couple more
being applied
seconds.
to it, like gravity, or?
Yes, we always assume it's gravity. We assume a normal room.
So you can't
Closing
do like
out.
that if you're going like
Okay, a very drastic response. All right, so one of the things that defines a liquid is that you do have the particles moving past each other. You still have some attraction between them. The molecules will have some sort of interaction. They're polar molecules, and you're going to have intermolecular forces pulling them together that are stronger than if they're nonpolar. So they're together, gravity pulls them down. They fill the shape of the container as gravity pulls them down, but there is movement. What about the third one? Is this a true statement? A sample of gas, the molecules are not moving. Gaseous water. Couple more seconds. Closing out. All right. Same answer as last time, is the majority of the class responds, is that those molecules, it is false, they are moving. So is it just the same as in liquid? They're moving faster, and what's different about their movement?
It's more random.
It's random, sporadic, and it's not held down by gravity. It's the general kind of rule of thumb, right? So if you have a container and you have a gas in there, it's going to fill the whole container, as opposed to liquid water would settle down and be pulled down by gravity if there's extra room, right? So we're going to be spending a lot of time talking about these molecules today here. And I think that that's our learning objectives for today, is I want us to more and more in depth be able to visualize the difference between interactions, solid, liquid, and gas molecules. And we're going to start off by describing what pressure really means. It sounds exciting. It actually is really exciting. Spend a little bit of time talking about temperature, pressure, and number of moles of molecules related to the ideal gas law. And then finally, we're going to predict the flow of gas in respiration and also in beach weather. Okay. Let's take a look at a definition of pressure. Which one of these two do you think is the best definition, technical definition of pressure? And maybe let me see if this works. We're zooming in on part of that balloon that has gas inside of it. A couple more seconds. All right, we're closing out. I kind of gave this away a little bit by the diagram that I showed, and hopefully you've done it in lab, and maybe it was in your primer. Not sure. I can't remember if it was in the primer. In order to measure pressure, we have to measure collisions. You can't just be like, the pressure is, and like get a feeling for it, right? So the way that pressure measurements work is that you go to the side of a container, you put a probe in, and you say, if I had a really, really, really sensitive hand, and I put my hand, little micro hand in there, how many particles hit my hand during a certain amount of time? How frequently do they hit? And how hard do they hit? That's pressure. So B is what almost everyone answered, and I agree that B is the appropriate response. So we have a sensor here. How many particles hit, how fast are they going, and how frequently are they hitting? That's our definition of pressure. So if we have that as our definition of pressure, then what happens to the pressure when the temperature is raised? So I'm going to change my simulation over here in a second to raise the pressure. But first I want you to answer, based on just what you know, what's going to happen to the pressure. If it helps, think about the definition we just made of what pressure is. Try to explain it to your neighbor based off of the definition we just had for pressure. So there's two ways to answer this question. One is a logical, like what have you observed happening? But I want to focus a little bit more on the second one, on the technical, chemical level, physical, really physics. How does our definition of pressure allow us to answer this question? Can I get a volunteer to share what you discussed? New voices. Heard a lot from the two of you, so I'm going to ask other people to share. Volunteers, please.
It gets hot, it wants to spread out.
Okay, when it gets hot. So Tara says when it gets hot, things spread out. if they're allowed to.
I was gonna say that when the molecules speed up, they'll be more energized, and they'll start colliding against the side of the container faster, and so the pressure increases.
So when you increase the temperature, you give things more speed. That's the chemical definition of higher temperatures, more kinetic energy, or more speed. So they're going to go faster. So let's take a look at our simulation. When we warm it up, now our gas molecules are moving much faster. So if you were to put your hand here, what are you going to feel? You're going to feel more collisions at a higher speed, higher pressure. So what if we were then to take the balloon at our increased temperature and then increase the volume? We're going to expand the balloon. What's going to happen to the pressure inside the container then? Think about why. Can you describe why?
This is assuming that the balloon is expanding because of us and not because of the pressure.
So take a note for the why part. We're going to walk around and I'm going to see what you're writing for your why. Question 5. So we said that you're moving. Okay, make sure you click on your response.
Okay, I got a question. So I'm putting more in there, but they still going that same way.
There's no more in there. We're just letting the balloon expand. All right, does anyone want to answer this question with a molecular description of why? So what's the answer and what's the molecular description? With new voices, please. Shelby, I see you raising your hand.
I said because like with more room, it would take longer for it to climb to the sides, so it would take more time to slow down, decreasing the pressure.
So I agree with almost everything you said except the last little part. You said it gives them more time to slow down. If they maintain the same temperature, they're going the same speed. Granted, not every one of these particles is going the same speed, but the average speed is going to stay the same if we maintain the temperature. But what we're doing is by expanding the balloon, making it a little bit bigger, now it takes, like you said, longer for everyone to get across and collide with the side. So we're going to have a lower frequency of molecules colliding with the side of the container or the pressure sensor. Is every single gas molecule moving at the same speed?
If they hit each other.
Does anyone, have you played billiards before, pool? Played pool. Billiards? Is billiards not a normal word?
Billiards is a word,
If you're
there's plenty
British,
of people who
billiards,
call it
if you're American.
billiards.
So I want us to think about the molecules
Full billiards, it's like
Similar
50-50.
to balls on a pool table. And if you were to give it a certain amount of energy, right, a certain temperature, and you collide with those balls, you're going to have all the different balls moving at different speeds. The more energy you put in, the average speed is going to be higher, but some balls are standing still at any one point in time. I think we looked at animations of this earlier in class. Yes?
Yep.
So we look at some animations, and at any one point in time, you can find something that's moving still, but the higher the temperature is, the more of them are moving faster. The average speed is higher. And I think that the majority of our class says that our pressure will decrease as you increase the volume. So what would happen if we added more molecules into the balloon? Would pressure go up, go down, or stay the same? Why would it go up? If the temperature stays the same, we have more molecules, so we have more collisions at the same point. You guys just described the ideal gas law. As pressure goes up or volume goes up, you're talking about more collisions that totally was not an accurate statement, was it? Does this formula look familiar? PV equals nRT. So if we're talking about pressure, what happens to this? If we don't change the temperature or number of molecules, as this volume goes up, pressure has to go down. Mathematically, we can justify that. If you keep both of these constant, the pressure and the volume, but you add more molecules, N, the right side of the equation gets bigger, so does the left side. If we change temperature, whatever change happens here has to change the pressure as well. So the relationships that exist in that equation describe exactly what you thought of. So if there's ever a question mathematically about the ideal gas law, make sure to think about the logic of it first. Think about the little particles moving around and whether it makes sense to answer the way that you are.
What does R stand for?
R is the gas constant. And I used to have a slide in here for question number 2. If you're at standard temperature and pressure, you can actually calculate R based on the pressure of 1 atmosphere, the volume of 22.4 liters, N is 1 mole, temperature is 0 degrees Celsius. So you can calculate R. It's a proportionary scale. I'm not focusing on it in this class because we don't have time. Okay. So with that said, remember I said that gases don't take up, they expand to fill their space completely? Well, then we wouldn't have an atmosphere. They are affected by gravity a little bit. And I don't know if you've ever thought about this. You know when you go up in an airplane and they're like, oh, it's low pressure, right? And the door can fly off because it's higher pressure in the plane than out of the plane. Atmospheric pressure, I want you to think about all the gas molecules that exist in the atmosphere directly above us. The gravity of all of that pulling down is just like in a swimming pool. If you ever go down to the bottom of a swimming pool, your ears pop because it's higher pressure. Because all that water is being pulled down on top of you. Atmospheric pressure is the same exact thing, except instead of water that's really dense, it's gas that's not very dense. And so all the gas that's above you does have a little bit of weight, and it pushes down on us. The higher up in altitude we go, the less air we have above us to push down on us. So if you were to go up to Denver, then you have a little bit less pressure than we have here. We're almost at sea level. So we have 1 atmosphere of pressure. You go up a little bit higher, it's actually 17% less pressure. That's pretty significant. That means that you have fewer gas molecules around you if it's the same temperature. If you go up to Bolivia, you have 62% of the pressure. If you go all the way up to the top of Everest, every 1 breath you take only has 30% as many molecules in it as if you were down here. That's why you have to be in such good shape to climb Mount Everest, is because you have to be capable of functioning on 30% of the gas molecules you normally would. You ever think about atmospheric pressure like that, all the gases around us? I didn't until I started teaching this.
It's harder to breathe,
The higher up we go, every breath only gives us 1/3 as many molecules if we're at the top of Everest. So we'd have to breathe 3 times to get the same amount of oxygen into our blood system as if we're down here.
But if you're conditioned to it and they made it up to the top, how long do they stay up there? If they like build little houses where they can't actually stay up there?
There's a lot more to it than just that factor, but you don't want to stay up there for very long. So one of the units that, I think one of the questions in the pre-class primer was about units of pressure. What is higher pressure? Just like talking about weight, I can say how much I weigh in pounds or in kilograms or in ounces or grams. I can use lots of different units. Pressure has a whole bunch of different units as well. And so these are all the different units. So we have a ton of conversion factors. So on an exam, I could give you this table, and I could ask you the same type of question as a primer. Which of these is higher pressure? You would just need to say, well, let's put them all into the same unit so we can compare them.
Hypothetically on the exam.
I will give you this table on the exam, yes. So there will be homework questions that I will put up tomorrow morning that will have you converting between different units of pressure.
We use torque already.
Yeah. Yes, the conversion factors are in your book, or you can Google them. I will be due, I was trying to decide if it's Sunday or Monday. I'd kind of like to have the post, I need to think about it. It'll either be due Sunday at the end of Thanksgiving or Monday after the last class.
You don't have to if you don't want to.
Those two. I think there's a lot of people in this class that would like an additional opportunity to practice and also to increase their grade in mastery. Okay, let's talk about breathing and application of gas laws.
Okay.
So based off of the image here, you can kind of pinch with your fingers and zoom in. Look at all the different components. Which one of these is the best representation of Skeletor exhaling?
And you've got him covered
And think
up.
about multiple reasons why.
You've got him covered up. This-
Wait.
I think most people submit a response. Last I checked, it was 50-50. Check the person next to you. Point out details.
I've gone back this time too. It's not that it's a whole more thing to do situation.
Somewhere like this.
We've never done it around.
Okay, what are the things we're looking for in these images? We're talking about exhaling. There's some really obvious ones and there's some not so obvious ones.
What's in the
What about the chest?
When you inhale, you know that you're filling your lungs with air. So
Okay.
that means doing it bigger. So when you're exhaling that out, then your lungs would contract.
Okay, so we need to have a decrease in volume of our lungs in order to exhale. And so, how did you see which one of these does that? I guess on the right side you have both of these pushing inwards. Is that the idea? So you said that that's exhaling. What are the really obvious ones we can tell from this diagram?
My arrows going out.
Okay, there are also arrows showing air moving out. But I want to think about more than that, okay? So in this diagram, when we compress our chest and our diaphragm compresses at the same time, then we're exhaling. So let's dig into that a little bit deeper. And I can't remember if... Do I have a little... Doesn't actually do it? Ah, it used to be a GIF. Okay. It was Skeletor.
So if you're trying to strangle Skeletor.
Okay, so let's go ahead. I think was that the front page?
Or how about like if we like cover his mouth, we're like not letting him
So we're going to be really mean. We're going to plug his nose and mouth, or maybe he does himself, right?
Yeah.
And I want you to think about the pressure inside of the lungs when his chest expands and his diaphragm is contracted. So if you want to test it out yourself, you can go ahead and do it on yourself. Think about our definition of pressure, what the molecules in our lungs are doing. What that looks like.
this. I can't remember the answer.
You can't breathe.
So what do you think is, you know, like, your pressure, like, why we, how we're.
If you find that the patient decides to stop breathing,
Yeah, once it's pressure, just do it. How is the pressure in greater
Okay, make sure your clicker response is in. going to go ahead and close this out. And we do not agree. All right? Does anyone want to argue? Do you want to try first? Do you want to do it first? So, cover your hand over your nose and mouth and try to compress, or sorry, we're expanding your chest. We're contracting your diaphragm. So think about what is the result when you remove your hand, and why is that?
Nothing.
So what does that mean? What's happening to the pressure inside of our lungs? And why? I don't know. I heard someone talking over there. Who wants to share?
It was me. I see it greater because first time I was like, when you cover your nose and your mouth, like you feel like a pressure in your chest, like you need to breathe. Well, that's you breathing in and out is relieving that pressure. So when you cover your nose and your mouth,
So
obviously the pressure.
I'm gonna ask you to totally change your definition.
No, I mean
We don't need to breathe in and out. We generate breath in and out. So how? That's what the question is really about. Is how do we generate the force that dictates the movement of gases? Donald? Thanks for raising your hand.
Howdy. Okay. I'm just gonna guess here. So when you have exhale, your chest is at pressure, and when you inhale, it's above pressure, which happens to equal out.
I think we're oversimplifying a little bit. So let's just look at the exact moment that I'm talking about. If you cover your nose and your mouth, and you expand your chest, what's happening to your lungs? They're trying to expand. Your lungs are trying to expand. So that means that the molecules, if your lungs are expanding, what happens to the gas molecules in there? Are they hitting more or less frequently? Less frequently, because they have more space now. So they're moving the same speed, but they have a larger volume to cross before they collide inside the container. So as we're doing that, if we keep our nose and mouth closed, in this particular scenario, if we expand our chest, then the pressure inside of our lungs is less than it started with right before. Okay?
But that's only if it expands and we put our hand over it so it
Chest expands.
But we put our
hand over it and it can expand.
It does. It does expand slightly. It can't go too far because our lungs aren't that strong to pull a huge difference. So then what happens? On the opposite side, we close our mouth and nose with our hand, and then we go through this picture where the chest is contracting. What can we say about the pressure of air inside of the lungs? A couple more seconds. Closing out. All right, would someone like to talk about the physics of this answer? We have 3/4 of the class in agreement. I want to talk about the physics of this answer. Bradley?
So for every reaction, you have an equal and opposite reaction.
Okay, so you're choosing the opposite answer. So you want to talk about the chemistry of what's happening when you close your nose and your mouth and you compress your chest. What's happening to the pressure inside of your lungs, and how does that compare to what's outside of your chest? You know, would you like to volunteer to share your thoughts?
Please say
you're relieving pressure by exhaling with all of that gas and a lot of the molecules. So you're relieving the pressure inside of your lungs, so that it's going to be less than the pressure outside because it's pressing down.
So what's interesting is that your answer and a couple of the answers tonight are about what happens after you remove your hand from your nose and your mouth. I want you to think about the exact moment in time. Sorry. My bad, Carmen. Okay. At that moment where I'm pushing and I'm compressing my chest, what's happening to the volume of my lungs? It's getting smaller. So what happens to the gas molecules inside? They're bouncing into each other faster. They're colliding harder, not harder, more often. So at that point in time, we have generated a scenario where we have two bodies of air, inside of our lungs, outside of our lungs. There is no unnatural force that makes gas go between our lungs and outside the world. The only reason the gas flows from inside of our lungs to outside of our lungs is because of difference in pressure. If we create an area of high pressure inside of the lungs, where is the air going to flow to equalize that? It's going to flow out. If the higher pressure is outside of our lungs, where's the air going to flow? Back in. So the only reason that air flows in and out of our bodies is because we actually change the pressure inside and outside of our lungs. So is there ever a time where our lungs are the same pressure as outside?
When you've expanded and filled your lungs with air,
In the middle. What do we mean in the middle? Kind of combination of your two answers.
when you're maintaining the breath,
When you're between breaths.
you're maintaining it before you start
When
singing.
it's completely open, right? I don't have any physical barrier between my lungs and the outside. If the air is not flowing in or out, we have completely equal pressure between the two. That is atmospheric pressure. In order to get that air out of my lungs, I have to somehow increase the pressure inside my lungs so that the air between the two chambers, the world and my lungs, will come to be equal. I do that by compressing my lungs. That creates a higher pressure body of air inside of our lungs. That equalizes with outside. How big of a difference do you think that is? Is that like a really big difference in pressure? Is it like 50% greater outside than inside or inside than outside? You know, we talked about 2 units of pressure. We said atmosphere, right? 1 atmosphere is kind of atmospheric pressure. That's what we have here or there. And then that's also known as 760 millimeters of mercury. So 760 is atmospheric pressure. When we breathe, if we're sucking air into our lungs are about 755 millimeters of mercury. You realize how small that change is? That itty bitty bitty little change in pressure. What is that? What percentage is that? 5 out of 760? It's like almost 0.05% change in pressure is what all of our breathing comes from. And when we're running hard, how do we get it to go faster? If we change that volume quicker, we end up with a much bigger change in volume over time. So we can get a lot larger volumes of air to go in and out. So here we're talking about, based on this discussion, an increase in volume will directly relate to what in pressure?
What was the answer for that one? Number 9? What ended up being the answer that was? So you're saying it's greater than it?
A couple more seconds. Closing out. right. Based off of a whole class vote, if we increase, I think it was increase the volume, right? If we increase the volume of our lungs, at least a decrease in the pressure. So, can you write very clearly, do I have a spot for this? Question 11. Try to write a very clear statement on your own first, that's the think part, that describes what is the driving force for breathing. Once you've written a small statement, pair it with someone else, and then I want to hear a few responses.
You said for what?
Question 11 is this question.
I got a 58, and I was really hoping that I got I was not going to do it for the 28. Have a 79.
Oh, okay.
Like all of a sudden there's like a flying paper.
I was like, I only have one. I was like, I hope you did think of one. Okay, can I hear from a new group that hasn't shared yet today? What is the driving force? If we were to summarize this, the driving force behind breathing. Is that you raising your hand, Olivia?
It was distressing, but I can. Okay, well, we have like different answers, but my answer is hypoxic drive. Like your CO2, yours tells you that you need to take in oxygen.
That's good.
Okay, very true. So then let's get to how our body actually does that. So that's the biochemical pathway that drives the next step. So what's the next step then? Alexis, since you... Interesting. Okay, so that may be a component of it. Let's think about the conversation that we've had today and how those things contribute. So what is the actual driving force for air going in and out of your lungs? Andrew?
I said the physical change in volume of our lungs.
Why is that the driving force for air going in or out of our lungs? Pressure.
Pressure.
Oh, sorry, I meant like I'm putting pressure on you, but yeah, actually pressure is... Can you maybe restate that as a full sentence, including pressure?
So, yeah, the physical change in volume of our lungs to allow an increase and decrease of pressure to allow more oxygen to go in or out.
So I think the one missing component on a lot of people's papers when I walked around, what I saw was pressure. That the pressure inside your lungs is different from outside of your lungs. And that's true, but that's not how we drive that change. That's what we need in order to have air move from one place to the other. It's really about a lot of factors that result in our lungs changing volume through muscular contraction, either compressing or expanding of our lungs. That change then messes with the pressure in our lungs, and then the world tries to get to an equilibrium. So we try to have a physical equilibrium, the same pressure inside and outside. So that slight difference in pressure between inside of our lungs we generate, if we're expanding our lungs, draws air in. Or if we compress our lungs and change the volume to be a little bit smaller, that pushes air out. So it's always about the balance between the two. I heard a very interesting term earlier this semester from someone in the nursing program. They said they have these negative pressure rooms for tuberculosis patients. Does that sound familiar?
Yeah.
What does that mean? What's the pressure in one of these rooms?
The air is pulling into the room.
You mean what's the actual number?
What is the pressure in a room that is negative pressure?
The same.
Probably less than 7.
Is it 0? Is it negative 20? Is it...
Doesn't it mean it to be a little bit lower than outside so that it's easier to breathe?
So actually the negative pressure, this is not my field, I'm not 100% sure this is what it means, but I believe the reason for these containment areas is that tuberculosis is transmitted by breathing, so it's airborne. So whatever air the person infected breathes out, you want to trap. You don't want it just going everywhere, you want it going through a filter. So these negative pressure rooms are actually a little bit lower pressure, maybe 755 millimeters of mercury inside that room. That means air is always flowing from outside the room into the room. And then from that room, you might have one next door that's 753 millimeters of mercury. So the air flows from that room through a filter into the even lower pressure room. The term of negative pressure that kind of concerns me is that people think, oh, it's really like negative. Like you can't have a negative pressure. 0 pressure is no gas molecules. So it's always about negative means slightly less. So we create a negative pressure in our lungs when we inhale. That's how we get air to go in. That's actually what's used if you've ever done biochemical research. If you're working in a sterile environment, they also have these laminar flow hoods that you work underneath, and that also does the same thing. It's about the pressure differential. It can maintain a flow of air that's always sterile that you're working in. So let's take this and let's use it for a second to think about weather patterns. Have you guys ever seen images like this? So a lot of times being stuck in the middle of the country, we don't really think about what's happening here as a global phenomenon. But winds around the world act the way they do for a couple of reasons. One is because the world is constantly rotating. But the second is because heat changes the density of air. So we've been talking about what happens to pressure in an enclosed system. The air is not really a closed system, right? If we were to heat up this room, air would move faster in here. It would increase the pressure. The air would flow out of this room. Pressure would go down to the same. So the flow of air moving between two different places kind of helps equilibrate that. But there's this super cool website, nullschool.net, that allows you to kind of look at different places and where the current weather patterns are. So the color shows us the speed. So where there's higher color, there's a higher movement, and so right now we have a lot of wind coming off the Gulf of Mexico, which is why it's nice and warm. You can go back and look at historic perspective as well. I think that there's a part of this where you can go look at any date and time, and you can see what the currents were around the world and how they're all connected to each other.
What's going on over the Caribbean?
I'll put it in my slides, and it's linked in there so you can check it out. So let's talk about that for a minute. Let's say it's vacation time. We're done with the semester. We're going to go down to the Gulf Shore, right? We're standing on the beach, and our feet are in the sand, and we're facing out towards the Gulf Shore. If we're at the beach, let's think about the relationship of the air over the water versus the air over the land. Kind of thinking, and we're at the border, right? There's air over the water, air over the land. Which of those bodies of air is less dense in the middle of the afternoon on a warm sunny day like this?
Is there any land?
We're standing with our back to the land, so right at that border. Is the air over the land more dense? Or, I guess less dense is the question here. Which one is less dense, the air over the land or the air over the water? Or are they the same?
And also, it's like
Crazy record been hitting me.
A couple more seconds. Meh. All right, so we don't know. What are factors that might contribute to this? Actually, let's do it this way. I'm going to give you the answer, and then I want you to justify why. So which is less dense? Okay, so now that we've read the question right, and we know that air over the land is less dense, why? Go ahead and talk to someone around you. Try to think about, justify why. Heat waves?
Heat waves, that's it.
Okay, so let's think about this. We can start off kind of general. I do want to get to the chemical description, though, of why. So who wants to start off saying why it is the air of the land is less dense? Bradley?
So
You can't do the other one now because there hasn't been another one.
okay, so you may or may not like this answer because I'm going to give you a kind of physics-based answer.
Okay.
So whenever you're over the water, before you actually get to the ground level, you've actually got a more area above you, so then you'd have more pressure above you. So you'd have the water and the air pushing down, which would give you more density.
Are you talking about the relative height in that stack of air above you?
I guess. I don't really know where I'm going with this.
Okay, so I like that you're thinking up, though. It's really important to not just think about where we are. The pressure comes from what's above us, but also a couple other factors. So who wants to add to that? Jocelyn?
Well, I was thinking, it's funny that you got water evaporating, and even though it's the ocean, there's still some water evaporating, so there's more gas over it.
Okay, so one of the really interesting things is that if you do some calculations, and we're not going to do in this class, having water as part of the mixture of air actually makes it less dense. Although it feels muggy, it feels like it's really dense air, it's actually the opposite.
Whoa.
Thinking about just weight per volume. So that's a bit of an interesting concept. But the air over the land is still less dense. Why? Tay, what were you talking about?
Heat waves.
Okay, what about heat waves?
Like when you're on the beach and you can see, like from the sun, it's like you can see the heat waves. So I was just thinking that air would be more dense.
More or less dense? Okay, so you're saying that the air over the land gets heated by the sand. We know that because some of us might have seen heat waves. We know that hot air rises. So what about the molecular perspective? What happens when you heat up sand that's sitting underneath a whole bunch of air? It moves a lot, and then it goes to create higher pressure, but there's nothing holding it in. So it expands. So the number of gas particles you have there now have more space, which is less density. So then based on that answer, if you have air over the water, which doesn't get warmed up nearly as much, versus over the land that gets warmed up a lot more during the day, which direction is air going to move? Well, sorry, first question is, which body of air will rise where the two meet? And then there's the next question that I asked them. So this one is specifically if you're standing between those two, based on the density of the two bodies of air, which one is going to rise?
So you were saying that air that was filled with humidity is actually less heavy than normal,
Less dense, yeah.
less dense?
It's because if you calculate the molecular weight, every single molecule of water is 18 grams per mole. N2 is 28 grams per mole. So it takes up the same space, but it weighs less. It's going to be less dense. All right, closing out. So, based on the discussion we just had, which one of these two is going to rise? The one over the land, because it is warmer, it is less dense, things that are less dense rise. Okay? So then the last question on that is if you have the two bodies of air. The air over the water is cooler, it is more dense. The air over the land is warmer, less dense. Which direction are you going to feel air moving? If you're standing right there, facing the water, is the air going to be blowing towards the land, out towards the water, or is it going to be standing still? You want to take a look at an image that kind of describes this? So as midday heat, right, the land is much warmer. The air expands over the land, but the air over the water doesn't much. So that high density air pushes in to kind of fill the space that's left by the warm air. What's crazy though is that because this is moving inward, then it creates a vacuum out a ways offshore that pulls in air, and so you end up with this kind of cycle. Does that happen all day long? So this is what's called a sea breeze. If anyone's been to the beach, you get a sea breeze during the day. That's a sea breeze. So then, when does that not happen? Why? Why is that not happening at night? If this is colder over land, if it cools down a lot quicker than here, you're going to have the exact opposite flow. And at the time when they're both the same temperature, you're going to have the same between the two. And I think that I even have, it doesn't work, little animation to show that. So
you're saying though that water takes longer to absorb the heat than the land does?
Because water has a much higher heat capacity, it means it takes a lot more heat to change its temperature. The air over either one are not going to be changed as much over water. Okay, so take home. What do I want you to be able to do for an exam on this? I want to give you a scenario that talks about gases in a particular context, either breathing, sea breezes, or another context. And I want you to be able to say, based off of what you know to be true of gases and how pressure is measured, what's going to happen if a system changes. If you have two systems beside each other, that sort of thing. So we will spend a couple of minutes on nuclear chemistry. I wanted to spend the last 5 or 10 minutes of class on it. But nuclear chemistry is something I'll probably have a few questions on, therefore it would make sense to make it due Monday night. My concern is if I make this due Monday night, is everyone going to wait until Monday to do it? Or are you going to be studying for the exam and practicing early? I want you to have most of it done by the time we come to class on Monday, because it is going to be a review day. It's a time where I want you to be able to practice with almost all of your studying already done. Is that fair? Okay, so any more questions? You come talk to me if they're individual or...
Friday is our last week of section.
Friday's what? Oh, study session? You're doing a Friday study session?
Mm-hmm. Friday.
There will also be a study session this Friday. Is anyone likely to come to study sessions Friday? Run by our lovely LAs. Raise your hand if you would come to study sessions Friday afternoon and evening.
It's 2 to 4 and then 6 to 8. And it's the last one before the exam.
Would you come 2 to 4? Raise your hand if you come 2 to 4. Raise your hand if you come 6 to 8 on Friday. Granted, this is the last Friday before the break. Okay. Well, I'll send out an announcement. I just want to make sure that someone would be interested in going. I will not have my regular office hours on Friday because I will be out of town Thursday, Friday.
You don't come to class this Monday.